Yeah, thank you. Thank you for everyone who answered my greetings. And we see again today. And I'm starting recording the lecture today. At my place, it's raining like cats and dog. I'm not sure at your place. Is it so the same?
No.
Juga. Yes.
No?
Yeah,
Same.
the
And
sky is
heavy.
Di
dry.
negeri mana? Negeri mana yang tengah hujan sekarang ni?
Melaka, Melaka.
Melaka hujan. Lagi?
Selangor.
Selangor. I'm also in Selangor. Which part of Selangor?
Putra Heights.
UiTM.
Putra. Right. Shah Alam. Okay, the same. Close. I'm in Shah Alam as well. Putra High is quite close to me. Okay. Where else? Ada Sabah Sarawak. Kalau tak ada jawapan tu maksud tak ada lah tu. Alright. So let us start our class right away. We will, as usual, we'll start our class with the reciting of dua, and we would like to have someone who would buka doa, and then we will recite the doa together. Do you have the doa with you already?
Yes.
Okay, very good. I'm going to let the floor be yours now. Who will start the doa pembuka?
I will start the
Okay, Mr. Akasha, thank you so much.
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم الحمد لله رب العالمين حمدا يوافي نعمه ويكافي مزيدا يا ربنا لك الحمد كما ينبغي لجلال وجهك الكريم وعظيم سلطانك اللهم صل على سيدنا محمد وعلى آل سيدنا محمد اللهم اغفر لنا ذنوبنا ولوالدينا وارحمهما كما ربيانا صغيرا
Okay.
اللهم
Okay, we can
اجعلني
start
في
now.
قلبي
اللهم
نورا
اجعلني في
وفي
قلبي
لساني
نورا
نورا
وفي
وفي
لساني
بصري
نورا
نورا
وفي
وفي
بصري
سمعي
نورا
نورا
وفي
وعن
سمعي
يميني
نورا
نورا
وعن يميني نورا
نورا
وعن
ومن
يساري نورا
نورا
ومن
ومن
فوقي
تحتي
نورا
نورا
ومن
ومن
تحتي
أمامي
نورا
نورا
ومن
ومن
أمامي
خلفي
نورا
نورا
ومن خلفي
واجعلني
نورا
في نفسي
واجعل
نورا
لي في نفسي نورا
رب
رب اشرح
اشرح لي
لي
صدري ويسر لي أمري
صدري ويسر لي أمري واحلل عقدة من
قولي
لساني يفقه قولي اللهم افتح علينا حكمتك وانشر علينا من
من
خزائن
خزائن
رحمتك يا أرحم
رحمتك يا
الراحمين.
سبحان
Again,
ربك رب
Akasha?
العزة عما يصفون وسلام على المرسلين والحمد لله رب العالمين.
Amin, amin, ya Rabbal Alameen. Alhamdulillah Rabbil Alameen. We have recited the dua. I hope you do so at home. You do so the same at home. But next time, please, I forgot to tell you, we have to switch on our camera, and I could see you reciting the dua with me. Yeah, you can feel like it's like Juma'ah thing we ask from Allah. And now, without further ado, we will start our class with the lecture. And I have informed in the chat room that I have shared the lecture notes from last week and also for today in files. I hope you can find it. Have you found it?
Yes.
Okay, Alhamdulillah. You're all very intelligent. You know how to work around and search anything from Microsoft Teams, I guess. Now, so we will start with the sharing of my PowerPoint. I will share my PowerPoint now. Oops. Assalamualaikum. I am back. Did you lose me just now?
Yes.
Yes.
It was not because of the rain. I played with two screens today. I'm not sure with your class, right? Last week I got the echo, and this time I don't think I will get the echo anymore. But when I want to press my second screen, coincidentally the quit button came up, so I pressed at that button. So it was so funny. But anyway, all right. So I'm gonna share my screen again. Hold on. Hold on, yeah. Can you see my PowerPoint now? Anyone?
Tak.
Tak. Airan, Jaya. Dah nampak?
Still no, doctor.
Nampak ke screen PowerPoint?
Tak.
Nampak
Nampak?
lagi.
Nampak ke tak nampak?
Tak nampak.
Tak nampak, doktor.
Ish. Nampaklah pula. Apa ni sekejap ya.
Nampak dah doktor.
Ya.
Oh, lambat ya. Ya Allah. Dah nampak?
Dah.
Alright. So kalau saya move forward and reverse, can you see it's moving? Please tell me. Is
Yes.
it moving?
Yes.
Alright. So we are in order. Do you hear any echo?
No.
No.
All right, excellent, super. Now, so we will start our class right away. Okay, so just a little bit of refreshing of what we have done last week. We did identifying the types of rate of reaction, yeah, with the reactants and products. So easy for you. Then we determine we identify the equation, whether it's reversible, irreversible, isothermic and endothermic, homogeneous or heterogeneous. And this is where we stop, yeah, the elementary and non-elementary. So I will go forward to the last slide that we did last week. It was on this slide, if I'm not mistaken. Was it in this slide? This one? Before we did our breakout room activities, right? I guess so. So that was the end of the last week, and now we will continue with this week. This is week 2, lesson 1. But then I have few more contents that need to be elaborated from week 1, which is topic 1 on the non-elementary. So this is again another example of non-elementary. So we have this 1 mole of CO, carbon monoxide, reacts with 1 mole of fluoride. The rate of reaction is written as such that the concentration of the CO is to the power of 1, which is the same as the stoichiometric, yes, elementary. Then the second one is the concentration of chlorine, which is not 1 mole as stated from the stoichiometric equation, but it's 3/2. So therefore, even though only one concentration term, which is not elementary, so the whole equation is categorized as non-elementary. So as not general. To explain about the rate of reaction, we can say that the reaction is first order. The rate of reaction is first order with respect to CO, because the power value here is 1 first order, whilst the rate of reaction is 3/2 order for or with respect to chlorine. As an overall, whereby you use the symbol N, where you summarize the power number, either A or B. It's up to you whether you write it as A or B, to the power of A or to the power of B, or to the power of alpha or to the power of beta. Doesn't matter whichever symbol that you use, as long as you understand that it's the power value, which refers to the number of order of the reaction. Simply by adding those two values, and you will finally conclude that the rate of reaction for this reaction is 5/2 order. Okay, so that is one of the example for the non-elementary. And the other one is the reaction between the 1 mole of hydrogen and 1 mole of bromine, producing 2 moles of hydrogen bromide. As you can see, the rate of formation, because we have here plus, and HBr refers to the product, so it's a rate of formation of the product. In this case, it's a little bit complex, where it is non-elementary because we have 2 components, and each of the components has the temperature dependent terms and the concentration dependent terms. This temperature dependent terms and also the concentration dependent terms. The only difference is that we have numerator and denominator for the equation of rate of formation of HBr. So for each of the numerator and also denominator has the temperature and concentration dependent terms. What we see is, let us look at the denominator. We have K1, and at the denominator we have K2. Those Ks, we have K1 and K2 just to differentiate between the 2 rate constant. Yeah, so those are the rate constants. Multiplied by the multiplication of the concentration dependent terms. For the numerator, we have CH2, concentration of hydrogen, to the power of 1. That is elementary. But the second term is the concentration of bromine, which is supposedly to be 1. But in this case, according to the experiment, the results shown that it's half instead of 1. So it's non-elementary. The same goes to here. We have this 1, 1, but still we have the denominator. But at least if even one term becomes is non-elementary, so the whole rate of reaction is non-elementary. And this is an example for a homogeneous reaction whereby it's one phase. So let us look at the another example of a complex rate expression between the nitrogen oxide producing nitrogen and oxygen. So again, we have this rate constant K at the numerator and K prime at the denominator. C, concentration of nitrous oxide to the power of 1, which is not the same as the stoichiometric, which is 2 moles, so therefore it's non-elementary. So this is again another complex rate expression whereby we have this numerator and also the denominator. Do you have any question before I proceed to the next slide?
No.
Great, thank you, Ms. Nornada. All right. Now, we will proceed with the next slide, which shows the complex rate expression of the nitrous oxide. But in this case, we are focusing on what happens if the concentration of the reactants or the product changes, either very low concentration or large enough. In this case, we are referring to the concentration of oxygen. And from that formula, I think I hear Azan, so we will take our few minutes break first until the Azan finishes, yeah? Okay, I'm back. Now, so where were we? Yeah, we were, can you hear my voice?
Yes.
Yes.
All right, great. So we are at this slide showing you what happens if we what happens if we analyze the rate of reaction based on the different concentration of one of the components. In this case, the first scenario is if at very low concentration of oxygen, and the second scenario if at a large concentration of oxygen. Yeah. If you look at the rate of reaction equation, of course, we have the K nitrous oxide and the K prime. Those two specific rate constants are strongly dependent on temperature, definitely, because we are referring to the Arrhenius equation. So the first scenario is if the concentration of oxygen, which is the C of the oxygen, the question would be, where do you see this concentration of oxygen in the equation of rate of reaction? Is it in the denominator or numerator?
In the denominator.
Right, thank you, Mr. Akasha. At the denominator, this is where the concentration of oxygen. So if the concentration of this oxygen is very low or so low that it becomes so insignificant, so what happens? If this concentration is very low, so what can you say about the C, the concentration of oxygen? What can you say? What can you assume?
It's very low in concentration.
Go on.
That's all. It's very low in concentration.
Okay, go on. So what can you assume with that in mathematical equation? So please take note now. I write here as R, which we have K and C over 1 plus K prime and C. All right. So the C is, let's say, A, which is this one. A becomes B plus C. So we have K of the A and K prime C of the C. Right? So the first scenario says, as you said, the concentration of the oxygen, which is CC, if it's very low, mathematically, what can you say from that equation? If this is very low.
It's negligible.
Yes, Kaira? Yes, very good, Mr. Akasha. It's negligible. You can as if neglect it, meaning you don't need this term anymore because it's so slow. So this so slow, so low. So this is what we say as it becomes insignificant, not important anymore, not significant. So therefore, the equation becomes minus R is equivalent to Kc over 1 plus 0, right? So what is left is Ka and Ca to the power of 1. When we have this equation, it means what can you conclude? Is it, what is the order of the reaction?
First order.
So first order.
Yes, very good. Ms. Kara and Mr. Akasha, it's first order. So this is what it says here. An apparent first order reaction with respect to nitrous oxide, and the overall itself is also first order. Yeah. So that happens when the concentration of oxygen is so low. So let us look at the second case or scenario. If at large enough concentration of oxygen, CO2, large enough, meaning in this case, minus R equivalent to K C over 1 plus K prime CC. This is large, meaning large enough, larger, even larger than 1. So large enough. So what can you say from this mathematical equation at the denominator? Can you neglect this term?
Cannot.
Can you neglect this term? Yes, very good. Cannot. So, but can you say it's like adding 1 means nothing? Right? Okay. So it means here the 1 is so insignificant because this second term becomes so big, as if even if you add 1, it is so insignificant already. Yeah. So therefore, K prime CO2 is so big, meaning the rate of disappearance of the nitrous oxide can be concluded as such that Kc, this is to the power of 1, then over, you can neglect that as if it means nothing, over K prime C to the power of C, which is also 1. So how do you calculate the overall order of reaction? The overall order of reaction is simply adding the power value for the concentration. So how many power value that we have here? One is for the NO2, N2O, which is nitrous oxide, and at the denominator, which is C, which is oxygen. Just add these two up. So how do you add those two up?
Dapat zero.
Dapat 0 sebab 1 plus minus 1.
Minus 1.
Correct. So therefore, what is the order of the reaction?
0 order.
Very good. So it's 0 order reaction when the concentration of the oxygen is large enough. So what you can conclude is that with this type of non-elementary homogeneous equation, the order of reaction may change due to the concentration of one of the components, in this case, oxygen. All right? So it's very common for liquid and gaseous reaction promoted by solid catalyst. So we will see the example of a gas solid which is heterogeneous in the next slide. And this example is for homogeneous reaction. So let us look at this, another example of non-elementary, whereby the benzene reacts with hydrogen with the presence of solid catalyst, producing methane, and also to form benzene, the toluene plus hydrogen to form benzene and also methane. It's a gas-solid heterogeneous reaction because we have all gases, but the catalyst is solid. So it's a heterogeneous reactions. The reaction order cannot be deduced from the reaction stoichiometry, but then we can take note that normally for a gas-solid catalyzed reaction, it follows the Langmuir-Hinshelwood kinetics. So this is maybe a new term for you to be heard. I'm not sure, but this is one of the model kinetics in chemical reaction, and particularly for the gas-liquid reaction. Yeah. Now, we are looking into the rate of reaction for the formation of benzene in the hydromethylation. In this case, you see that the rate of reaction for the benzene formation, if you write it as minus RT, then it means the rate of disappearance of the toluene is returned based on the multiplication of the concentration gradient, and this is the partial pressure, which indirectly showing or representing the concentration of gas. So normally, when you have components in gas forms, if we were to express it in terms of how much gas of gas A in the air, for example, so the best way to express the concentration of any gas in air or in any other gas is by expressing the partial pressure. So that is why you can see here the K is the temperature dependent term, and the second term, which is the multiplication of the partial pressure of the hydrogen and also the partial pressure of the toluene, are actually representing the concentration dependent terms. So in this case, this is again another complex rate expression whereby you have the numerator and the denominator. Denominator. Yeah. So take note, what you should take note here is, other than seeing the small k, which refers to the rate constant, and the partial pressure written in italic, yeah, so refers to the partial pressure. If you write P without the italic in capital, it's pressure or absolute pressure. But if you write it as italic, then it's a partial pressure. Another new terms that you may see here is, other than the P, what is that?
K.
Yeah, thank you, Miss Kyra. The K. And how different is that K in the denominator to the K in the numerator? Miss Kyra. Kyria.
I'm not sure.
Not sure? Okay. Who wants to try?
They
Excuse me?
are capital.
Okay. Small and little. Little and small. Kan sama ke?
Capital, Doctor, capital.
Oh, capital, yes. So take note, yeah, we have one K, small cap, is the rate constant. This is also rate constant, yeah. But in this case, the capital K refers to the adsorption constant. Yeah, you will see that in the next slide, showing you, since we are talking about gas solid. Gas solid. So remember, when we have solid, so the diffusion of the gas in your mass transfer, you see, is adsorbed onto the surface of the solid catalyst by the gas. That is why the capital K refers to the adsorption constant in kilopascal to the power of -1. Yeah. So let us go to the next slide, showing you the reversible reaction. The new thing that I want to show here, you have seen that in last week as well, the forward specific rate constant and the reverse specific rate constant. So we have a reversible. If you start with the B here refers to the benzene, the D refers to the diphenyl, the hydrogen refers to the hydrogen. So let us start from the left, whereby the benzene is converted to diphenyl and also hydrogen with a rate constant of K. Then here we put B, the rate constant of the benzene, and it's Kb. Since it is a reversible reaction, so the D and also the hydrogen may combine to produce the benzene in a opposite direction, whereby the K now, the rate constant is the K minus B. Yeah, since we want to use the same rate constant for the benzene, so therefore, if it goes to your right, then it's Kb. If it goes back in reverse, then K minus B. So the K minus B refers to the reverse specific rate constant. Now, in this slide, we want to learn how to write the rate, the specific rate of reaction, the rate of reaction, of the disappearance of benzene in forward direction. So rate of the disappearance of benzene is minus R benzene. Forward means the Kb, the rate constant, which is a temperature dependent term, times the concentration term, dependent term, which in this case is the benzene. Cb squared is simply because we have these two moles, with the assumption this is actually elementary reactions, yeah? So if we were to write the RB only without the negative symbol at the front, then you may bring the negative sign to your right, then it becomes RB forward. The question would be, why would I want to write this as positive? You'll see that in the next slide why we do that. Yeah, but we'll just hold on a second. So let us just proceed with, if we were to write the rate of formation of benzene in a reverse direction. Here, if you go forward, it's the rate of disappearance of benzene. Once you produce diphenyl and hydrogen, for a reversible reaction, we may also reproduce our benzene. So we can say rate of formation of benzene in a reverse direction. So the rate of reaction in a reverse direction with reference or with respect to benzene is defined as the reverse specific rate constant times the CD to the power of 1 times C hydrogen to the power of 1. All right. So the easiest way would be, we still use KB, but since it's reverse, K minus B. Then the concentration term, dependent terms, would be where it origins. Yeah, the same goes to here. It goes to your right. So the concentration dependent terms comes from the where it origins. Yeah, originally benzene, before it is being converted. Right. So this is the equation for the rate of formation of benzene in a reverse reaction. So what do we do with these two equations? We can use these two equations in the net rate of formation. Why we have net? Net is only applicable when we have reversible reaction, because we have two directions, forward and reverse. So we need to know the rate of formation of benzene. Here, of course, we have benzene forward, then benzene disappears. If it's reverse, benzene forms. For the net rate of formation of benzene still, but we use both of the rate of reaction. The RB forward, take note, the benzene plus the RB reverse. Take note, in this equation, there is no negative sign. So simply the rate of reaction forward and the rate of reaction reverse. From what we have derived earlier, the rate of reaction forward is this one, yeah, where you started with the rate of disappearance, yeah, then it becomes negative here. So simply replace that here plus the rate of reaction reverse, which is positive from the beginning. So simply add those two terms, then it will give you the net rate of formation of benzene for the reversible reaction. Do you have any questions?
Me, no.
No, thank you. All right. This is the slide that you have seen earlier from the Arrhenius equation. And now we want to write or rewrite the equation. Let's say if we have two conditions with the same reaction mixture, let's say you have Ca in there, both are the same, the concentration initial are the same in those two reactor number 1 and reactor number 2. The only difference is that we have different temperature, T in reactor 1, T in reactor 2. So how to write the Arrhenius equation with the assumption at the same concentration but at different temperature? So that would be our problem statement. So what we do is we write the rate of reaction for both conditions. One for the condition number 1, 2 for condition number 2. Yeah, we're having K1 and K2. With the assumption the temperature 1 and temperature 2 are not the same. whilst the concentration 1 and concentration 2 are the same. So how do we do that? We will be using the Arrhenius equation. Simply write the Arrhenius equation. First, having those two equations, why not we arrange the equation such that R2, the equation number 2, divides by R1. So you have K2CA2 over K1CA1. Since we know CA1 and CA2 are the same, you can simplify this by saying, let's say it's CA. So what you see here is this is CA, CA. Yeah, it's the same thing. CA. So therefore, K2 over K1 is equivalent to R2 over KR1. Here, we will use a simple rule of this mathematical equation of y is equivalent to the exponent x. Simply convert it to another expression. It becomes ln y is equivalent to x. So here, we are going to ln both sides. So ln both sides. So you will get, if it's ln K2 over K1 or ln R2 over K1, simply as the same as ln K2 over K1. So substitute this by the Arrhenius equation. And finally, the simplified equation is minus E, which is the activation energy, over the R, which is the universal gas constant, times 1 over T2 minus 1 over T1. Yeah? So that would be one example of expressing the Arrhenius equation for same concentration but different temperature. Okay? Do you have any question? No. Okay, that would be the end of the topic 1, which is the continuation of last week lecture. So we will proceed with week 2. Do you still can proceed or you need a break?
Five-minute break, Doctor.
Okay. Okay, thank you, Mr. Akasha. We will take our 5 minutes break, yeah? So welcome back. Are we ready now?
Yes, doctor.
Right. So we will proceed with topic 2. So this is the first slide for the topic 2 in week 2. As you see on the screen, we have the lesson plan as you received from the beginning of the class, whereby now we are in week 2, and supposedly we'll start with topic 2. And the topic 2 is entitled The Determination of Rate Law. And we have batch reactor data interpretation and batch reactor data analysis. It simply describes that when you have any reaction and you want to go for the production of any products, you need to know how much yield or how much product that you want to use, or not to say not only that you need to know, but you want to plan for how much of that production. For any reaction, of course, we have learned earlier in topic 1, it's very important to know about the rate of reaction equation. What is the rate of reaction? The order of the reaction. Having said that, how do we know that we can calculate this rate of reaction? And or as you know, how do we know to write the rate of reaction equation? So it comes from the experiment in the laboratory. Having that experiments, you have a collection of data. So with that data, you need to know how to interpret the data. So this is what we're going to see here in this topic 2. I refer to Levenspiel, and from that textbook, Levenspiel, you can refer to chapter 3, and also the Fogler in chapter 3 in that textbook, and together with both the Fogler and also the Levenspiel in chapter 5 and chapter 3 respectively. And to start with, we will start with the interpretation of data. But first, when we want to start our experiment, we will start with the batch reactor. So as you know, the batch reactor is what you see here. There is no continuation of lines, yeah, or the feed, inlet and outlet. It's simply what you have in the reactor. The reaction mixes and reacts. Yeah, so that is batch. And from that batch reaction in a batch reactor, we can later on relate the conversion to the reaction. The symbol for conversion is capital X. The symbol for reaction rate is R. So the assumption that we can use, or we, not to say we can use, we use, yeah, it's much easier, is to use a constant volume reaction mixture in the batch reactor, whereby as time goes by, T1, T2, T3, T2, T here is referring to the time, yeah, T small t. As time goes by, the concentration, let's say A1, CA2, and CA3 will also change. And the change can be either decreasing or increasing. So if A is the reactant producing B, as time increases, what would happen to the C, the CA? Since A is the reactant, what would happen to the CA?
Become lower.
That's right, it becomes lower. Decreases, correct. Siapa yang jawab tadi tu? Tak nampak nama? Daniel ke?
Aja, Dok.
Oh, Raja. Thank you, Mr. Raja. Yeah, so as time increases, the concentration of the reactant decreases. So if I go back to my previous slide, we are assuming the reaction occurs in a constant volume batch reactor and with a varying concentration as time increases. Yeah. Now, Now, so this slide shows you what can batch reactor do. It can produce specialty chemicals. It is primarily used for homogeneous reaction. Homogeneous means if it's liquid, then everything liquid, yeah, homogeneous. So we can use batch reactor, and it can be used for a small scale. Then the reaction data which are collected are assumed to be at a transient state. Transient state means this is transient, yeah. You are collecting data at different time, yeah. So that is transient. However, each collection of the data at each time, it is assumed that the concentration at that particular time is representing the concentration of anywhere in the reaction mixture. Yeah. Why? Because in the batch reactor, we have impeller. So that is the purpose of having the impeller, because it mixes the reactions around. So therefore, even if you take out your sample here, or you take out the sample here, or you tebuk kat sini ke, you ambil sampel ke, or tebuk kat sini ke, you ambil sampel ke, since we have the impeller mixing the reaction homogeneously, then the CA here, the CA here, CA1 here, 1 is referring at T1, yeah, are the same, yeah. So this is what it means by uniform composition everywhere. But composition changes with time. Even though anywhere you take that sample at, kata ada 4 spots, yeah. So the second time we take CA2 at T2, here CA2 as well, here CA2 as well, here CA2 as well. 2 refers to a different time. So CA2 at 4 different places are uniform. But CA2 is not the same as CA1. So this is what it means, yeah. It means but the composition changes with time. So the reaction data are used for the determination of the reaction loss and the specific reaction rate constant. Again, not only that we use a constant volume, but we also make sure that our reaction is at the same temperature, because we want to use the same, we want to use the same R, yeah, considering only the change of C's, not considering the change of T. Okay, if you remember when we have this slide showing you what happens if we have 2 conditions with the same concentration but different temperature, then we need to, consider this this new formulation of this rate of reaction equation due to the changes of temperature. So therefore, to simplify our findings based on reaction rate, we assume constant volume and constant temperature. Now, so this is the example of CSTR, whereby you have the impeller. And this is the right-hand side is the simplified schematic diagram. The left-hand side is a little bit more than simplified, but again, still simplified, you see. So the real drawing, engineering drawing for only one reactor is actually very complicated, yeah. So this is again simplified, both are simplified. But the right-hand side is more simplified, yeah. Here in your DP1 and DP2, design project 1 and design project 2, when you reach your final year, if you are responsible to design a reactor, of course, you kena design your kaki, you have to design the cover of the reactor, you have to design the height, you have to design the diameter, you have to design how length is your diameter of your impeller, the height of this impeller thing, which shape of that impeller, and so on. Whether you have 2 levels or 3 levels of impeller, yeah, every scenario have to be considered, as what we mentioned in last week's lecture. Yeah, the fluid mechanics, the thermodynamics, the heat transfer, the mass transfer, and this one, this class, reaction engineering. Now, so we are getting into more serious business here. As what we say, we want to produce as much product as we want. So the product comes from the reactant. So therefore, the key word here is how much of the reactant is being converted. So the term that is used is conversion. Yeah. If you're talking about how much is the conversion of the reactant A, then you write XA. Let's say that is your stoichiometric equation. A produces C or D. If the A is limiting reactant, yeah, there are two components, A and B. The A is considered to be limiting in comparison to B, whereby A finishes first, or it's very limited, it's in demand, highly in demand. So A is limiting reactant, it is best. So if we were to express how much of the A being converted, so we want to know how much of B needed per 1 mole. So therefore, the A over A, then everything divides by A. So we will express our conversion based on per mole of A basis, the limiting reactant. So therefore, always remember when we write our conversion, it's always based on the limiting reactant. In this case, if A is limiting reactant, then we want to express the conversion of A. So that would be the basic idea. How to write the formula for the conversion of A? Simply knowing that moles of A being reacted, because we want to know how much is being converted. So how much mole of A per mole of A fat? This means initial. So we have the original, the A decreases. So how much of A reacted over the original, which is the initial? Yeah. So we have two cases. If it's irreversible, meaning not reversible, then the maximum conversion is 1. In this case, it refers to what? So let's say if we say XA is 1, what does it mean?
100% conversion.
Apa?
100% efficiency.
Yes, 100% efficiency. Tadi semua orang jawab at the same time, Mr. Afsar, Miss Khairia, and Mr. Akasha. 100% efficiency. 100% efficiency. Again, Mr. Akasha, 100%?
Yeah, 100% efficiency because everything is converted by the term.
Okay, Mr. Akasha, you use the word efficiency.
Yes. 100%
Okay.
efficient.
Yes, 100% efficient. Haha. Okay, ada ke terms tu dalam science? Okay, who wants to try? Siapa lagi nak tambah?
100% conversion.
100% conversion. Okay, who else who wants to add? Khairia? Tadi tiga-tiga ni nampak nak bercakap. Miss Khairia, anything you want to add?
Sama macam Afsar.
Oh, sama macam Afsar. Okay, 100% efficiency and 100% conversion. Both would mean differently. Yeah, efficiency would be related to, if you were to compare efficiency and effectiveness. But in this case, we are talking about how much of moles being reacted from the original, being consumed. Meaning, specifically, we want to focus on how much of the A being converted. So 100% conversion. Efficiency would mean how efficient the A is being used. Yeah, how efficient. That will be a different engineering scenario, aspects that can be more elaborated between efficiency and effectiveness. All right, Mr. Akasha, I will take some time to actually find an example of efficiency and effectiveness in other time. Yeah, please remind me. Okay. Yeah, that will be another interesting topic when we use the word efficiency and effectiveness. But in this case, we would like to specifically focus on conversion. Okay. Now, for reversible, since it's reversible, the maximum conversion is here is also maximum. Yeah, the 100% is equivalent to the equilibrium conversion for the reversible reaction. We will see that in the few future chapters, yeah, later on. Now, so this is again another important point of conversion, yeah. We want to express the conversion in another expression. There are two expressions that we would like to express in. One is the mole of A, the reactant consumed. The other one would be the moles of A in the reactor at time T. So let us start with the first one. How much of the A consumed? The A consumed because it has been used, right? In order to relate this equation by the X, so we are going to use this conversion X in the equation. So the X is simply multiplied by the initial concentration of A. So if you were to write the X, it means mole of A reacted over moles of A fed, which is initial. That is simply the Na naught, initial concentration of A. So simply multiply by the Na, meaning this is Na naught. This is Na naught. All right. So you'll get moles of A reacted or consumed. Okay. So the other equation would be how much of the A in the reactor at time T, meaning Na without the T here is to refer at any time T. Simply the initial minus the consumed. Here is the consumed. Na naught X. So how much of the A left or in the reactor at time T is simply the original minus consumed. The original minus consumed. Okay. So you'll get the concentration of A at that time T. Simply Na naught minus Na naught X. Okay. So simplify that equation, you'll get this expression. Na naught times the open parenthesis 1 minus X close parenthesis. Now, so we're going to use this equation in the stoichiometric equation for a batch reactor because we use the batch reactor for the data collection to determine our order of reaction and specific rate constant and so on. We know that this is the mole balance equation, which is the Na, the moles of A at any time T is equivalent to simply the original minus the consumed. Now, the question would be, what is the change of moles of A in the reactor per unit time? Change of A per unit time. Simply change of A, this is change of A, dNA per unit time. Is equivalent for a batch reactor is equivalent to the specific rate, the rate of reaction times the constant volume. So the constant volume, yeah, the rate of reaction times the V. So that would be the expression for the change of A per unit time is simply the rate of reaction times the volume. So if we were to minus it, because we have this expression, yeah, the rate of disappearance of A, yeah, minus RA times V is simply that expression, whereby this whole thing is equivalent to the K, CA, CAB. With the assumption it's homogeneous and elementary, yeah, can be said homogeneous, but mainly it's elementary, yeah. And another assumption would be the reaction is perfectly mixed, meaning you have the impeller, it is being mixed homogeneously, then we say perfectly mixed. Due to the perfectly mixed mixture, then of course no variation in the rate of reaction. Before this, we were talking about sampling taking out. We have CA at different spots, then the CA is assumed to be uniform everywhere. The same thing as R, due to the perfectly mixed reaction, all right? Now, we have that more balance. Okay, now we want to determine how long to leave the reactants in the reactor to achieve certain conversion. Meaning, we have different X, yeah, with different time. Let's say T naught, which is T, let's say 0 second. So the X is 0, all right, because that's the initial time. As time increases, then what happens to the X? What happens to the X?
Increases.
Yes, decreases. So here it asks you how, let's say this is what you want, yeah? Let's say 70%. So what is this time? So how to determine the time for a specific conversion value? So to start with, we can start with the more balanced equation. Then we differentiate with respect to time. Here we have NA is equivalent to original minus consumed, right? And if you were to differentiate through time, meaning differentiate it, d over dt, d over dt, d over dt. All right. So you have dNA over dt is equivalent to d over dt of NA. NA is constant, so you don't need to differentiate constant value. Yeah. So simply 1 over dt. Okay. Then we have NA naught still. Then we have X. X, yes, it varies. So dx over dt. And we know that NA naught over dt is constant because the initial value is constant. So therefore, the constant value being differentiated is always 0. So you can simplify that to 0 as what you see here, minus the second term is equivalent to dNA over dt, which you see from our previous slide. The change of moles of A per unit time is simply RAV, the rate of reaction A times V. So this is what you see. Yeah, it's equivalent to here NA naught dx over dt. NA naught dx over dt, since you have negative, then bring it over, then you have negative RAV time, not time, is equivalent to NA naught, NA naught, NA naught, NA naught times the open parenthesis dx over dt, close parenthesis. So that would be the equation, basic equation to start with when you want to determine the time in a batch reactor system with a volume, with a constant volume, constant temperature. Okay. Now, having that, we have this equation for a batch reactor system. We are going to find the dt, the time. Simply rearrange that. Okay, then you'll get this equation. So it started with the time is equivalent to NA naught dx over minus RAV. If you want to find the time, so simply differentiate. Now, integrate. So you have integration of the d time from t something to t something. So normally starts from the t naught, the initial, to the final. At t naught is always, since we are integrating dx, so from x to another x. Since this is t naught, so at t naught, which is at 0 second, for example, the x is considered to be 0 because the reaction hasn't started yet. So we have X naught, which is 0. So that is why you have 0 there. Yeah. Okay. Then T here at that time is always X. That's why we have X there. So this expression is used for you to determine the time needed for the reactants to leave the reactor to achieve at certain conversion. All right. Now, you see here two curves, left-hand side and right-hand side. The left-hand side is for A component, the B-hand side is for the B-hand side, the right-hand side is for B component. For the equation A to B, the A is the reactant. Of course, the A decreases through time. So that is why you see it's being decreases exponentially. Same goes to B, whereby B is a product, so the B increases as well, right, through time. Now, let us look at this slide showing you the case where if we want to write the rate of reaction, assuming constant volume batch reactor. We have done that from our previous slide. Now, simply, we want to express the rate of reaction in terms of constant volume. So we know this is where we started with, yeah? Remember, we have this reactor. Then we know that the change of mole per unit time is actually RA times V with a constant volume. So this is constant. If you were to write the R, so simply rearrange that. So that is why we have 1 over V. DNA over D time equals to RA. Okay, so this is what you see. And the V is considered to be constant. V naught is actually the same as V everywhere because V is anywhere, anytime. Yeah, because V is considered to be constant. So here we have V 1 over V naught, then D and A over DT. Okay, so it combines this, yeah, into this equation. And from that equation, we can simplify the NA over V naught, which is equivalent as concentration. You know that the unit for concentration is mole per liter. And that mole is referring to N, and that L is referring to V. So if we are talking about A, so NA over V is simply the CA. So that is why we rewrite the equation as rate of reaction is equivalent to dCA over dt. Tian, you tak nampak muka I lupa nak tukar. Dah nampak ke muka? Tak nampak muka. Korang dengar ke saya cakap ni?
Dah nampak dah. Dah nampak dah.
Tak cakap, tak nampak muka. Ya, saya tengok kamera. Sampai tak ada orang nampak saya. Saya lupa nak tukar. Anyway, penat-penat saya pandang je kamera tapi tak ada orang pun nampak saya. Okay, anyway, so we have this rate of reaction. Okay, this is where we stop. The rate of reaction is dCA over dt. If we let it be negative at both sides, yeah, because we are talking about the rate of disappearance. So we have minus dCA over dt, and that C is expressed by the ideal gas law, right? Whereby we have the C is equivalent to P over RT. Okay, where do you get this? C, actually it comes from PV is equivalent to nRT. Then we have N over V is equivalent to P over RT. And the number of moles over the volume is C. So that is why we have C over T is equivalent to P over RT. Yeah, this one. So this is ideal gas law. So we replace that ideal gas law formula into the C here, and this is what you express based on the constant volume batch reactor for rate of reaction. Okay?
Okay,
Right.
Doktor.
Same thing, the same equation. You have this rate of disappearance of A is simply the change of concentration per unit time for a constant volume. So this is as simple as that. For a constant volume, simply remember rate of disappearance of that reactant is simply minus dCA over d time. And that is simply equivalent to what you have learned earlier, which is the K times the C. Since we have A two products, so you only have one CA, yeah? CA to the power of alpha. In this case, alpha is here, all right? Alpha. Doesn't matter if I write A or alpha, you know, it's the same thing. If I forget to change it, but you understand what it means, yeah? Okay. Now, we talk about, we want to go into the real business, right? So we want to write the conversion. So this is where it starts. Basically, previously was just the basic thing. Now we want to write the conversion X. How do we do that? The first step is the mole balance. This is your mole balance, right? Number of moles of A, original minus consumed. Then you derive the X. So from here, you get what X. Then once you get this equation, step number 2, you relate X to C using this assumption, yeah, this C assumption, and of course, constant V. Finally, you differentiate XA, all right? So we'll do that one by one. So let us start with this one. We have the mole balance. We have the mole balance, right? Then you rearrange the equation by XA. Simply rearrange this equation. This is what you got. Then we want to express the X and relate it to C. How do we do that? We know that C is simply the N over V. We have this equation. Let me write this equation. This is simply NA naught minus NA over NA naught. Okay? This is simply 1 minus NA over NA naught. You can try writing it yourself as well on your piece of paper. Here is simply the X, right? The step says that we want to relate the X to the C. So how do we do that? We don't have C in this expression. There is no C. How to write this creatively, but still the same meaning from the mathematical expression, simply by divides each of the term by the V. If we do that, this one, NA over V over NA naught over V. Would it still be the same as this one? Would it be still the same?
Yes.
Creatively, when we write that, it will give you the same expression. When we do that, we know that the NA over V is C. NA over V is C. The only difference is that this is NA over V, this is NA naught over V. So this is CA naught, this is CA. Okay, so this is what happens. All right, so 1 minus CA over CA naught. So this is what it means by relating the expression of X to C. Okay, then the last step is differentiate XA. So we differentiate both sides. Yeah, dxa. D, if you differentiate 1 is 0. Then you differentiate the second term. dCA, oops, right? dCA times 1 over CA naught. CA naught is always considered to be constant because that is the initial concentration of A. All right. So what is left is minus dCA times 1 over CA naught. So that would be the expression of the change of X in the reactor in relationship to the CA naught, the initial, in relationship to the change of concentration of A. Right? So what happens is that when you collect your data, so at different time, T1, T2, T3, we have CA1, CA2, CA3, and then we also have X1, X2, X3. As time increases, the X increases. As time increases, the X increases. As time increases, the CA decreases. So this is what you see from the final equation. Okay? All right? So that would be the first part. Very good. So that would be the first part of our batch reactor analysis today. So we have some more, but since I intend to actually proceed with your breakout activities, we can continue with that, but maybe we have some more time to actually talk a little bit more. Are you still okay if I were to go forward with more complicated stuff, or you wanna proceed that in the next lecture?
I'm okay, Doctor.
Okay, Mr. Akasha, what about the rest?
Me too.
Okay, Doctor.
Okay.
Can
Okay,
still go
I will
on.
proceed. Okay, go on. I will proceed with a little bit more. I think I will stop until here. Yeah, because as you go a little bit more forward, starting from this one, it will be very complicated because I have to explain very detailed, yeah, in this case, yeah. So if I were to rush, then you will not be able to understand quite clearly. Okay, let us proceed a little bit more before we go to our breakout rooms, yeah. We'll stop at 5:45. Okay, we'll try our best. Now, so we'll proceed with the second part of the topic 2. We talk about data interpretation, meaning we do our experiments. And then when we do our experiments, we want to do our experiments. The question is where? We will do that in a batch reactor. And what is the assumption that you can make? The assumption that we can make is, oh, saya pula duk cerita. Baik, saya tanya kamu. We want to do our experiment. So we go to the lab and then we want to start our experiment. We have 2 components. We want to run the experiment in a reactor. So you choose, in this case, you will choose which reactor according to our lecture today.
Batch.
Batch reactor.
Batch reactor. In batch reactor, great, excellent. In batch reactor, you have your batch reactor. What would you control?
The temperature.
The temperature. So you are saying the temperature is constant, isothermal. Some more? Some more? Asfar? Afsar.
The same as Kalia. Constant volume.
Yeah, the same volume, the same as Kalia. You sebut siapa? Kalia?
Kai.
Okay. Oh, Karia. Suara mikrofon Karia ni macam saya tak dengar ataupun saya seorang yang tak dengar. Orang lain dengar.
Saya dengar sebelahan juga.
Okay, so maksudnya telinga saya okay lah. Alright, so Karya maybe want to check with your microphone ya, tak apa dengar. Okay, very good. So we in the lab we have reactor, then we want to control constant temperature, then we want to control constant volume, meaning the volume of the reaction mixture is constant. Then what do we do? Kita pun start experiment. So we are talking about data collection kan? So you collect data, panggil nama lah. Collect data macam mana? Panggil nama lah, asyik orang yang sama je jawab. Masyitah.
Ya, doktor.
Mana Masyitah? Masyitah?
Ya, saya.
Tu, kita buat okay, buka lah video. So kita collect, we collect our data kan? So what do? You want to express your conversion. So what do?
Like
Masyitah.
concentration
Okay, you collect concentration at
with time.
Yeah, with time. Meaning time differently. You ambil lah setiap sejam ke, setiap 2 jam ke. If the reaction is so fast, maybe tak boleh lah tunggu sejam 2 jam. Maybe every 2 minutes. Yeah, every 50 seconds, why not? Every 1 minute, you take data. So the conversion will change. So then once you have the data, this is what you see in this second part of our topic. We have a collection of data. I am forwarding my slides here. So you have a collection of data. So this is what you see at different time and the concentration. So the next question would be, you take a sample. How do you know that concentration? How do you know the concentration of certain component?
Using equipment.
Using equipment, very good. So we use analytical equipment. Maybe in your power plant, some of very sophisticated and highly advanced technology, the sample are taken automatically and directly connected to the analytical instruments. You can get the concentration of any component based on certain analysis. Yeah, for example, HPLC, it can be HPLC, it can be FTIR, it can be TGM, it can be whatever analytical instrument, chromatography. If we are dealing with gas chromatography, we can, it's not an easy task, yeah, it needs some calibration, but basically those are the things that we can do. So from here, we interpret the data. You can still see my PowerPoint slide, right? Okay, but by interpreting this data, there are methods of analysis to interpret the data. Yeah, this is what we are going to start with. On your right hand side are the examples of the methods. You can use either integral method, differential method, initial rate method, half-lives method, or the least square analysis method, or the other word we call it nonlinear regression method. There are many methods that we can use to analyze the data. All right. The data acquisition, as you mentioned, is taken by the data collection task based on concentration at different time in a batch reactor, transient meaning at different time, then or the concentration measurement in a differential reactor for a steady state reactor. So let us start with analyzing the data because you want to determine your reaction order or your specific rate constant. There are steps for you to follow in order to determine those two important parameters. First, you can start with postulating the rate law. Of course, you have learned from last week until today how to understand the rate of reaction equation, for example. And which kind of law that we can use. In this case, we will look at the future slides. And the second step would be you choose your reactor system and you write your mole balance, the one that you write or learn just now. Third step is to process the data based on the measured variable, so which which concentration of a component that you choose as your measured variable. From that, you simplify whatever that you can simplify. Simplify means any constant value. Yeah. For example, we did today, if the concentration are the same, concentration in condition 1 and concentration in condition 2 are the same of that particular component A, then simply write CA rather than CA1 and CA2. So this is what it means by simplification. And final step would be, then only we can determine our reaction order and specific rate constant. Yeah. Now, for a homogeneous reaction, we can follow power law model, and heterogeneous, we can follow Langmuir-Hinshelwood model, as what we mentioned earlier. Power law is simply because we have this concentration to the power of certain value. And that value is alpha, which comes from the stoichiometric. Yeah, so simply power law. And Langmuir-Hinshelwood, which is more suitable for a gas-solid reaction, is simply expressed due to the partial pressure, and we have K and also the absorption constant. Yeah? Same goes to the second example, whereby we have this Ca alpha and Cb beta. For batch reactor, this is what you know earlier, which is the rate of disappearance of A is simply for a constant volume. For a constant volume, simply remember, is simply the change of the concentration per unit time. For differential reactor, we will do that in our future chapters, where this is just to show that we also have differential reactor. Yeah, for now we are still touching on the batch reactor. All right. So how do we do that? So that is step number 2. This is step number 1. Postulating the rate law. You choose either power law model or the Langmuir. So normally the Langmuir-Hinshelwood is learned in your reaction engineering too, yeah, because we are dealing with the gas and solid together in Langmuir-Hinshelwood by using Langmuir-Hinshelwood model. And as far as I remember, we do that in your reaction engineering too. Okay, this is reaction engineering 1. Then the third step would be, once you know that you run your experiment in the batch reactor system, for example, in this case, as our example, you can write your mole balance in terms of the measured variable. And once you have your mole balance based on the measured variable, you can identify which reactants are in excess or limiting. Yeah. If one of the reactants are in excess, assume the concentration is constant. Meaning this is the thing that you want to identify before you go to the next step, which is step number 4 for simplification. Meaning, once you assume here, there is a simplification equation that you can write with the assumption, right, means tulis, with the assumption that the concentration is constant because it is in excess, meaning dia banyak sangat, dia bukan limiting. Bila dia banyak, yang limiting tu yang nak habis kan, selalu nak habis, produce your product. But in excess ni macam seolah-olah tak bergerak-gerak. Macam tu sebab dia in excess, banyak sangat. Penggunaannya sedikit dibandingkan dengan the limiting reactant. So that is why we can simplify the assumption when that particular component is in excess, yeah, which you say the concentration of the excess component is constant, right? This is where you start with the determination of reaction order and the specific rate constant. All right, I think I will finish this slide before we proceed in more detail. Meaning, let's say if you have equation number 1 and equation number 2, the equation number 1 is simply the rate of reaction equation for A becoming B. The B is the product, the A is the reactant. Simply write the rate of disappearance of A is simply the Ka times Ca alpha, right? For a constant volume, as I told you, you can say that the rate of disappearance of A is simply minus dCA over d time. Then we relate 1 and 2, meaning 1 and 2 can be related, yeah? Because this is minus RA and minus RA. So K minus Ka Ca alpha is equivalent to dCA over d time. Since this is minus, then simply bring that to here. Now, having that, we learn both sides. Actually learn the minus RA, learn the minus RA. So ln minus dCA over d time. So actually this is also ln. So using the simple rule, ln minus Ka Ca alpha is simply ln K plus alpha. Bring it over, alpha ln Ca. All right. So this is where you start to use different methods to solve for the alpha, which is the reaction order, and the K, which is the rate constant. If you look at this equation, it resembles the linear graph. You have the x-axis and the y-axis, whereby the left-hand side is your y is equivalent to mx plus c. I'm not sure how you learn it in your SPM, but the x is the x-axis. In this case, ln Ca. The y is actually the ln minus dCA over d time. The c, which is the intercept is the c, which is ln K. C is ln K. And the m here is the slope. This is slope, which is the alpha, the slope of the straight line, the linear line. Yeah. So from here, you can use different method. The first one will be the graphical method or differential method. The second one is numerical or finite difference. And the third one is the integral method to determine your K, which is the specific rate constant, and your alpha, which is the reaction order. All right. Okay, so I would stop here. I think it's very late in the afternoon already. Whether you go to your breakout room or we want to adjourn our class to the next meeting.
Not sure, Doktor.
Apa dia? Tak dengar orang lain lah pula cakap. Saya nak tanya nama orang lain. Saya nak tanya Nur Syafiqah. Apa kita nak buat sekarang?
Sekarang ke doktor?
Apa dia?
Doktor kata nak buat yang
Saya tanya soalan, nak go to your breakout room ke ataupun you nak berhenti di sini, adjourn our class to the next meeting.
setelah perbincangan dengan roommate saya kata dia nak
Ada
macam gini.
Ada roommate rupanya. Mari kita tengok roommate dia siapa. Nur, siapa jawab tadi? Nur Syafiqah kan?
Roommate saya Nur Nada.
Nur Nada. Okey, Nur Nada mula-mula bising lepas tu diam. Nur Syafiqah pandailah saya panggil Nur Syafiqah dengan Nur Nada. Alright. Who wants to join our class? Raise your hand.
Marilah kita berehat doktor.
Tengok Akasha angkat tangan. Rehatlah. Afsal kata, oh ramainya. Alhamdulillah, mereka tak tidur. Mereka angkat tangan. Lega. Kotlah. Tiba-tiba dengar berdengkur. Alright. So we'll see again. Is it Wednesday?
Thursday. Kamis.
Thursday. Thursday afternoon.
Yes, Thursday afternoon.
Thursday morning tak ke?
Thursday morning. Thursday morning. Okay, pukul 10. So we'll see you again on Thursday at 10 o'clock. Kalau you perasan muka saya macam tangan masih laju tapi mata macam nak tutup. Saya mengajar pun nak tutup mata. Macam mana? Orang yang dengar saya tak tahulah. Teringat zaman saya umur kamu lah. Zaman saya umur kamu saya punya power masa tu Ciwa ada power.
Oh ya.
Kelas macam tidur. Ada kelas macam tidur tapi 4 flat. Macam mana tu? Tidur dalam kelas tapi 4 flat.
Ustaz.
Sebenarnya dia bukan tidur. Memang mata dia kuyu. Okay, anyway. So this virtual class, the virtual class I lagi tak tahu rupa you macam mana. So anyway, I hope everyone is still awake even if kalau you tertidur tu perkara biasalah. Alright. So we'll see you again on Thursday at 10 o'clock in the morning Assalamualaikum warahmatullahi wabarakatuh. Have a nice day ahead. Bye.
Bye-bye, doktor.
Thank you, doktor. Bye.
Assalamualaikum. You're welcome.